Yeah, so before I start, do you have any questions about last time? So last time we discussed this dimension and dimensions, and we also saw linear maps, and we saw some properties of linear maps. Yeah. So so we saw some kernel of a linear map is a subspace, and the image is a subspace, and we had a formula as well. Yeah. So today we will see. So we saw a typical example of a linear map is given by a matrix. Yeah. So if you want to, if you have a m cross n matrix, it sort of defines a linear map from Fn to Fm. Yeah, where F is the base field. So today we will see that this is a typical example, meaning any linear map is between finite dimensional vector space is like this if you fix a basis. Yeah. So maybe we'll start with this, and then slowly we'll see more properties of linear maps and so on. Okay. So let's. So let phi be a linear map from the vector space V to vector space W. So these V and W are assumed to be a finite dimensional vector space over a field F, and let B be a basis consisting of V1 to Vn, and C is a basis consisting of W1 to Wn. Okay. So here, when we say these are bases, it's not just a set, yeah, it's also ordered. So if you change the ordering, things will change. So now onwards, when we say this is a basis, we mean an ordered basis. Okay, so the ordering is also fixed. B is a basis for V, and C is a basis for W, respectively. Then since phi is so phi of Vj is going to be some element of W, right? So since C is a basis of W, we can write phi of Vj as some linear combination of Wi's, which we denoted by, so phi of Vj is Aij Wi. Yeah, so it looks a bit funny, but I suppose it's okay. Yeah, so you can write it as some this where okay, so I forgot the most important. So where AIs, so J is between 1 and n, and AIJs are in the base field F. Yeah. So we can do this for all J between 1 and n. Yeah, and this gives us a matrix, M cross n matrix, because there are m I ranges from 1 to m. Yeah, so there are m rows and j ranges from 1 to m. So you get a m cross n matrix, and this matrix is called the matrix of phi with respect to the basis B and C. So it depends on this linear map phi on the basis B of V and the basis C of W. Yeah, so it depends only on these three. So this is the definition of the matrix of P with respect to these two bases. Yeah, so you guys have seen this, right? Yeah, so once you fix a basis, you get of both the domain and the target, you get a matrix out of it, out of a linear map. So that is all we are doing. Yeah. Now, so what is the relevance of this matrix? So you can sort of write this linear map in terms of the matrix if you use these bases as so you remember, once you are given a basis, every element of the vector space will have a coordinate. Yeah. So if you use this basis to write the coordinate of every element, then this linear map will boil down to A. That is what the next proposition says. Yeah. So more precisely, so let V be a vector element of the vector space V. So V is a vector, and let X. So I'm writing this coordinate in a column vector. Yeah, so X be the coordinate of V with respect to B. So in our earlier notation, V is basically so this is the notation we wrote. Yeah, so this precisely means that V is summation xi vi. Yeah, that is what V equals x tilde B means. V is precisely summation xi vi. Well, remember xi's are in F. Yeah, so this maybe I should write it this that x be in Fn be the coordinates of V with respect to V. Yeah? And similarly, phi of V will have some coordinates with respect to the basis C, because phi of V lies in W and it has a basis C. So you can write down the coordinates of phi of V with respect to this basis and call that coordinate Y. Yeah. Then the proposition phi is basically a if in terms of these coordinates. Yeah, so in other words, a of a times this column vector x will give you the column vector y. Yeah, so phi and a is playing the role of phi. So phi transform V to phi V, and a transform coordinates of V to coordinates of phi V. Yeah. So this is the it may take long time to state it, but the proof is pretty straightforward. You just write down all the what all these means, and then it comes out. Yeah. So x is a coordinate of V precisely means V summation xj vj j equals 1 to n, and y tilde is a coordinate of phi v precisely means that summation yi wi is I equals 1 to m is phi v. Yeah. And so now we know that phi v. So phi v we know is so if v is summation xj vj, then you apply phi to this equation, the first equation. Yeah. Then phi v will become summation xj phi vj. But phi vj is by definition we have this definition. Yeah, so phi vj is, or rather definition of A rather. So phi vj we know is summation aij wi. Yeah, so we just encode that. So phi vj you replace it by summation aij wi I equals 1 to m, and then you do the change of summation. Yeah, so you put I first, I equals 1 to m, j equals 1 to n, summation aij xj wi. Yeah. So I just rearranging the summation, right? And now, of course, phi v is summation yi wi, and it's also this. Then by unique, since wi is a basis, this expression must be unique. Yeah. So that tells you that yi must be equal to summation aij xj. So here you are using that since C is the basis. Okay. So this now this is precisely matrix multiplication precisely gives you this. Yeah. So this statement precisely means that the column vector y is precisely 8 times x. Yeah. Is that okay? Yeah. So this I hope you may have seen it in earlier linear algebra course, but this is how you sort of find a matrix of a linear map, and this is what it means. So once you identify, so vi sort of gives you a way to write down coordinates for v for capital V, and wi gives you a coordinate system for the vector space W, and then this linear map P. If you use this coordinate system, becomes this matrix A. That is what this proposition says. Okay. Any questions? Okay. So of course one can ask what happens if you change the basis. Yeah. So if you change the basis B to some other B prime and C to some C prime, now of course the matrix will change, right? The matrix should change. So matrix will change, and you can even govern how the matrix changes. Yeah, because these are very explicit things. So you can even see how the matrix changes and everything. So all this is based on the same this particular principle you apply many times. So that's what we'll do next. Okay, so give me a second. Sometimes the internet now is not very good here. So let me try to. So yeah, okay. Are you guys still connected to me?
Yes, sir.
Okay. Okay, so because it's saying my internet connection is again unstable. So you can hear me clearly, yeah? Hello? Can you hear me clearly? Maybe it's no. Hello? Can you hear me now? Am I audible?
Yes, sir.
Okay, okay, good. So we are back on. Okay. So what happens if we change the basis? Yeah, so let's see. So let phi and phi be the same linear map. And suppose now we have two sets of bases. B is one basis, and B prime is another basis where the vectors are denoted by Vi prime. And C, and similarly for W, we have two bases, C and C prime. So we want to know, so let A be the matrix of E with respect to BC and A prime with respect to B prime C prime. So we want to know how A and A prime are related. So actually, A prime is going to be P times A times Q for some P and Q, some matrix P and Q. Yeah. So what is this matrix P? So P is, so here you think of P as a matrix of, so you think of the identity map on W. Yeah. That is, it takes W to itself. Yeah. Each element to itself. So identity map. Also, you can, so if you fix basis, then again you can write a matrix for it. Yeah. So P is the matrix of the identity map with respect to C comma C prime. Okay. So this is basically the change of basis matrix, which we discussed last time, right? Did we discuss change of basis matrix last time? No, maybe we didn't. Anyway, we will discuss it today. Yeah, but P is the matrix of identity W with respect to, so there are two bases for W, right? C and C prime. So you use C for the domain and C prime for the codomain, and define the matrix for the identity. Yeah. So in other words, so we'll see what, I mean, we know the formula, what it means. Yeah. So we, to prove the statement, we will see that we just have to write down all the formulas and it will come. Similarly, Q is the matrix of identity of V, identity map with respect to B prime comma B. Yeah. So if you take P and Q to be this, then you have this relation that A prime is P times A times Q. Okay. So, so that's the relation between A and A prime. So again, to verify, it's similar to this. You just write down all the formulas, what all these statements mean, and plug it in, and you get the answer. Yeah. So first, let's fix the notation. So let A be this matrix Aij's, and A prime be the entries of the matrix A prime is Aij prime For P, let the entries be Pij, and for Q, little qij. Yeah. So now, since A is the matrix of Phi with respect to BC, what the definition tells us that Phi Vj is same as summation Aij Wi, right? So this was the definition of Phi is called the matrix of A is called the matrix of Phi with respect to BC if Phi Vj is summation Aij Wi. Yeah. So we are just copying that down here. So phi Vj must be Aij Wi. Yeah, is that okay? Good. So similarly, phi Vj prime, we can, will be summation I equals 1 to m Aij prime Wi prime. Yeah, so this because Aij, A prime is the matrix of phi with respect to this basis B prime and C prime. So we'll have to use the entries of B prime and entries of C prime to define Aij prime. Yeah. So these two follow from the fact that A and A prime are matrices of phi with respect to B comma C and B prime comma C prime. Now let's try to analyze what does it mean to say P is the matrix of identity of W with respect to C comma C prime. So identity of W means if I take a vector in C, basis vector in C, so for instance Wj, then identity of Wj is Wj. Yeah, so Wj should be some linear combination of Wi primes. Yeah, so Pij Wi primes. Then only P will be the matrix of identity W with respect to C and C prime. Yeah, so Wj is so this P is the matrix of identity W with respect to C prime. Precisely means this. Yeah. On the screen, can you see yourself as well? This mini screen which is visible to me is also visible to you, or you see only my page?
The screen is
You only see my page, is it?
yes.
Okay, so I don't have to move. Sometimes I feel like the screen is bothering you as well. So I try to move it around. So then I can keep it here if everything is visible to you. Okay, so EVJ, this is okay. And yeah, so similarly, Q is the matrix of identity V with respect to V prime. V means if you take a jth vector in V prime, Vj prime, then you can write it as summation Qij Vi, because Vi's are the elements of V. Yeah. So I just copied down what A being a matrix of phi with respect to BC means, A prime being a matrix of phi with respect to B prime, C prime means, and P is a matrix. So these are the facts I've copied down. Yeah. So now let's try to build our case. Yeah. So we want to say that A prime is same as P times A times Q. So we use this phi Vj, or rather phi Vj prime. A prime is what is given. So we want to transform. So we want to get Aij prime in terms of PAQ. Yeah. So phi. So for each j between 1 and n, we know that phi Vj prime is something is off. Yeah, so this, yeah, so you use this identity Vj prime equals summation Qij Vi. Yeah, the last one which we wrote, and apply phi Vj phi to it. Yeah, so phi is a linear map. So all this scalars Qij will come out, and we'll get this phi Vj prime is summation I equals 1 to n Qij Pvi. Yeah, and now we will trace all this. Yeah. So now phi Vi, we want to write it in terms of Aij, A's and W's. Yeah. So, but remember this formula is with Vj, phi Vj, and we want to replace phi Vi. So you just have to change j to I and maybe I to some k. Yeah. So if you write it correctly, you'll get this is summation j equals 1 to n qij aki wk. Yeah. So the second thing should become I because we are writing phi vi as something. Yeah. Is this okay? This equality? This equality is fine. Yeah. And then again, this wk we can use this formula now. This formula now. Wj equals summation pij wi prime. So if you replace wk by using this formula, this so we already have got qij aki, and then wk if you replace, then pijs will also come. So if you so wk, so j you have to replace it by k, and maybe instead of using I, we use L, and we get wk is summation plk wl prime. L equals 1 to m. If you use this formula, yeah, and then we just simplify. Yeah, so now we change the order of summation and write everything together. So we want wl prime to be outside. So the summation for L equals 1 to m will be outside, and you get this double summation plk aki qij. So I've written this because we want it to be paq, right? The formula should be a prime is paq, right? But this double sum is precisely ljth entry of PAQ, this double sum inside. Yeah. If you want to compute the ljth entry of this product of these three matrices, you can check that this is precisely this double summation. Yeah. Okay. Times WL prime. So that, but we know that phi Vj prime is summation Aij prime Wi prime. Yeah. So that tells you that this PAQLJ is precisely the A prime LJ, LJth entry A prime LJ. Yeah. So hence we get that PAQLJ is A prime LJ. Yeah. So that tells you that these two matrices, so maybe I didn't write it. So hence, which implies precisely that PAQ is precisely A prime, the matrix A prime. If the LJth entry, where L and J are between 1 and m, L is between 1 and m, and J between 1 and n, they are all same for both the matrices. Okay, so that completes the proof of this. Yeah. So just remember that this is how the change of basis works. Yeah. So you need if you change the basis from BC to B prime C prime, you need to multiply by a matrix P, which is the change of basis matrix in some sense. But in these words is called the matrix of identity W with respect to C comma C prime, and similarly Q is the matrix of identity V with respect to B prime comma. Okay, makes sense, everyone? Any questions? So I'll make this smaller. There's nothing below this, yeah. And let you ponder a little bit more. So this is, yeah, now the change of basis matrix is coming here. So I hope it's still visible a little bit. Okay. So the matrix of identity V with respect to B prime V is called the change of, is also called the matrix of change of basis of V with from B prime to V. Okay. So in this above notation, Q is the matrix of change of basis from B prime to B. Okay. So if you change the basis from B prime to B, the coordinates will change as well. Yeah. So the coordinate, So once you give a coordinate, then the coordinates will change by this matrix Q. Okay. But to remember, this you can remember more easily via this. So what does this Q? So remember there is this formula. Yeah. So maybe I should write down this formula. So change of Q is the change of basis matrix from B prime to B. Precisely means this formula, which you can see on the left hand side as well. But maybe I'll write it bigger here. So you see this formula. This means that Vj prime is summation Qij Vi prime, Qij Vi, yeah, not Vi prime. I equals 1 to m. So this is what Q being a change of basis matrix means, yeah, from B prime to B. So this information you can symbolically write like this, yeah. So if Q is this matrix, then think of these VIs as some numbers, yeah. And if you multiply with Q, you'll get V1 prime to Vn prime, yeah. So this multiplication, this matrix multiplication, if you do this matrix multiplication using this formula, yeah, or if you do this matrix multiplication thinking of Q as these Qij's, then you will get precisely this formula, yeah. So this is one way of remembering. So this shorthand V1 to Vn times Q, this row vector times Q times is equal to this row vector, is a shorthand of remembering what is the change of basis, what does change of basis matrix means, yeah. So from B prime to B, then you have to put B prime on the other side and B on this side, okay. Is this okay? You know what I'm trying to say, yeah? You replace Q by this matrix. So you replace this by Q11, Q12, and so on, Q1n, and so on, Qn1 to Qnn, and do this multiplication, then you'll get precisely this formula, okay? That Vj prime, the jth entry is going to be this thing, okay? So that is what I'm trying to say. So it's a more symbolic because you know, VIs are vectors, not really scalars. But it's a good thing to it's useful to remember, and you know, these symbolic things can be even formalized later on if you do some. I mean, if you allow entries to be operators and so on. But let's not worry about it. Yeah. So this is the way of remembering what the change of basis matrix does. So it changes V1, V2, Vn to so this Vi primes. So this is the relation B prime to B. If you are changing, then the new vectors are V1 to Vn. If you multiply by Q, you get the old vectors. So, okay. So let Q prime be the matrix of change of basis vectors from B to B prime. So if you if you do the other way, from instead of going from B prime to B, you do B to B prime, then Q prime is actually the inverse of Q. Okay. So the change of basis matrix from B to B prime is the inverse of change of basis matrix from B prime to B, which of course intuitively is clear. Yeah, this is what should happen. And well, you can use either use this formula to prove it, or you can use the symbolic thing to prove it. Yeah. So remember, Q has this Q V1 to Vn times Q is V1 prime to Vn prime, because Q is the matrix change of basis matrix from B prime to B, and Q prime is the change of basis matrix from B to B prime. So you'll get so you'll interchange Vi and Vi prime and put Q prime here. Yeah. So you have these two identity. And from these two identity, if you substitute one in the other, so I guess V1 to Vn prime is V1 to Vn times Q, and V1 to Vn is V1 to Vn prime times Q prime. So you replace V1 to Vn by V1 to Vn prime times Q prime, and then you get this identity. Yeah. So that tells you that this vector is same as this column, these bases. No. So what you get is V1 prime to Vn prime is same as V1 prime to Vn prime times Q prime times Q. Yeah. So that tells you that Q prime times Q must be identity. Okay. So this is more symbolic. So this is symbolic way of seeing it. But you instead you should use this formula. Yeah. Vj prime is this, and Vj prime is this, and in terms of Vi, and similarly Vjs are in terms of Vi primes, but you have to use Qij primes here. Yeah, and then if you combine, you'll get that this product is identity. Yeah, so this maybe I'll leave it as an exercise. So do it using this formula. Okay, prove that this Q prime times Q is indeed identity. Okay. So that will tell you that, and the other way is also true. Q times Q prime is also identity. But anyway, it's a square matrix. For a square matrix, you know that if it has a left inverse, then it also has a right inverse. Yeah. So this proves that the change of basis matrix from B to B prime is inverse of the change of basis matrix from B prime to B. Okay, any questions? Okay. So now we'll see a result which maybe you have seen in, so you must have seen this as well, but I don't know what proof you have seen, but so we'll see both you can state this result in terms of matrices and in terms of vector spaces. And somehow thinking in terms of vector spaces makes the proof somewhat simpler. Yeah. So let phi be a linear map. Then this statement, what does it say? It says that there exists a basis vector of B of V and basis of C of W, such that the matrix of V with respect to basis BC looks like this. So there will be an identity matrix here and in one corner, and the rest are zeros. Okay. Okay, so this is the statement of the theorem. So let me just first translate it for you, what it means in terms of matrices. Yeah. So see, if V is a linear map, so if you fix some basis, or let's say V is Fn and W is Fm. Yeah. So if V is a linear map, means it's given by a matrix with respect to standard basis. Yeah. So what this tells you is that so the theorem tells you there exists a basis for which this this matrix is I000. Yeah. So what it says is that, so if I do a change of basis, so what it says is that, so if I choose a different basis instead of standard basis, if I choose a different basis of Fn and a different basis of Fm, then I can get to this matrix. But what does our previous theorem say? If we change a basis, then we are basically pre-multiplying by a matrix P and post-multiplying by a matrix Q, right? This is what it says. So, so if you apply that previous theorem, then what it says is that if A is any matrix, then we can find a matrix P and Q such that PAQ is I000. Yeah, where and in fact we can show that see, that is a change of basis matrix. Yeah, P and Q are change of basis matrix, and we saw that change of basis matrix are invertible, right? Q prime times Q is identity. So in fact, what you can say is that you can find PQ not just any arbitrary PQ. You can find PQ in GLN and GLM. Of course, if you take P and Q to be zero, then this is trivial. Yeah, you can always make it into a zero matrix. So it becomes non-trivial only if you insist that these P and Q are change of basis matrix. Okay. So this theorem is more or less this theorem is so the second part, in particular part, is basically a special case of this theorem when V is Fn, W is Fm, and phi is given by the linear matrix A. Yeah. Then once you know that there exists this thing, then you can apply the previous result and get it. So what we'll do is we'll prove this theorem. Yeah. So do you know how to prove this about the matrices directly? There exist P and Q as non-singular such that you can make it into this thing. What is the proof? How do you prove this? If I give you an explicit matrix, how will you do this? Anyone remembers? So you must, I'm pretty sure you must have seen this, but if anyone remembers, then that will be great. No, no one remembers? Okay, so so maybe if I tell you, you'll remember. So what you do is you do some row and column operations, yeah? So if you do a row operation on the matrix A, then you are pre-multiplying by a matrix, yeah, by a non-singular elementary matrix. And if you do a column operation, then you are post-multiplying by some matrix, yeah. So if you do row and column matrices operations, and you multiply by one of those elementary matrices which are non-singular, yeah. So you are multiplying by a sequence of non-singular matrices on the left and the sequence of non-singular matrices on the right. And by row and column operation, of course, you can make any matrix into this form if you are allowed to do both row operations and column operations, right? So for instance, you'll make the first entry to be, you'll take first non-zero and you'll change maybe rows so that the A11th entry becomes non-zero, and then you sort of eliminate, you make it 1 by dividing by something, and then you eliminate it and so on. Yeah. So you have seen this, right? By row and column operation, you can make any matrix into this thing. But that if you write in terms of matrix operation, it is precisely this. But that's a computational method. I mean, to say that you can do it is that it terminates, and you'll have to work out the whole algorithm and convince yourself that it can be done. But abstractly, the proof is even more simpler. So you can write it in just 2-3 lines. So let's do that, yeah. So yeah. So let V1 to Vn be the, so phi is this map. So I'll prove this this statement, yeah. We saw that this statement implies the in particular statement, and you know another proof of this in particular statement, yeah. So I'll prove this statement. So what do we do? So we take, we look at kernel of phi, yeah. Kernel of phi is a subspace of V. We start with a basis of kernel of phi, call it V1 to Vn, yeah. So kernel of phi will somehow not play any role in sort of formula for the matrix in some sense, yeah. So we shouldn't worry about this kernel of phi. But remember, if you take a basis of kernel of phi, you can extend it to a whole basis of V, yeah. So you extend it by adding some more vectors in V and call those vectors U1 to Un. And you write them first and then V1 to Vn. Yeah. So you extend this set, linearly independent set V1 to Vn to a basis of V. by adding this m more elements. Yeah. Sorry. So the numbers are not matching. Yeah. So let me rewrite, change the numbers. Yeah. Sorry. So V is capital V is supposed to be n dimensional. So let's call this V1 to Vk. Yeah, sorry. Let's call this V1 to Vk is the basis of kernel phi, and I'll add some number of elements. So I need n minus k elements. Yeah. So I'll instead of you introducing new guys, I'll just say n minus k. Okay, u n minus k elements. If I add, then total list becomes n, and that is a basis of V. Okay. So we extend it to a basis of V. Then remember last time we showed that the images of UIs in this dimension formula, we showed that the images of UIs. So then phi of, what did we show? U1 to phi of un minus k. What do we know about this? What can we say about this linearly, this set? This is contained in W, right? It's in fact contained in, is contained in image phi. Yeah. But what do we know about this set? So that this is linearly independent, right? So last time we showed that this in fact generates the whole of image, and of course then we showed that they are linearly independent, and hence it's a basis. Yeah. So this is then this is linearly independent. Yeah, and in fact it's a basis of image phi. So let's call this wi's. Yeah. So let's call this W1 and this Wn minus k. Yeah. So it's a subset. It's a linearly independent set in W. So again, we can extend it to a basis of W. Yeah. Is linearly independent by by this rank nullity or something. Rank nullity. Last class we, I don't know if I called some dimension formula or something, but that is called rank nullity theorem as well. So extend it to a basis of W. A basis W1. So so remember W has dimension m. So you'll go to n minus k, and then Wn minus k plus 1 to W. Extend it to a basis of. So this is our B, and this will be our C. Okay. So we have found our B and C, and then we just so now the matrix of, so now if you think about it, the matrix of phi with respect to B and C. What is it? So what do you have to do? You look at, so this is the basis of B, yeah? So you have to look at phi of Ui, and you write it as linear combinations of Wi's, yeah? That is how you have to do, right? Phi of Ui's and then phi of Vi's and so on. So, so what is phi of Ui? Phi of Ui is phi of U1 is W1, yeah? So if you want to write it as a linear combination of W1, W2, W3, it's just going to be W1, yeah? So the coefficient is 1. So you get 1 here, yeah? And the rest will be zeros. Yeah. Similarly, phi of U2 is just W2. So the coefficient of W1 is 0, the coefficient of W2 is 1, and the rest of the coefficients are 0. Yeah, so you get 0, 1, 0, 0, 0, 0, 0. Yeah, and so on until you reach n minus k. Yeah, so this is n minus kth spot. You'll get 1 here, zeros, and then the diagonal entry will be 1, and then again 0, because phi un minus k is just wn minus k. Yeah. Now what happens to phi of v1? What is phi of v1?
Zero.
0, right? Because vi's are in the kernel of phi, right? So phi of v1 is 0. So this whole column is going to be 0, and so on. Yeah. So this is 0, and so on. So rest is 0. Yeah. So this is precisely I n minus k 0, 0, 0. Okay. So remaining k will be 0, and here m minus n minus m minus n plus k zeros padded up on the right. Okay, so that completes the proof of this proposition, this theorem. Is that okay, everyone? Okay. Okay, good. So as you can see, this thinking in terms of abstract way. So we didn't, we just used ideas. Yeah, we didn't do any computation to prove this. We just used the ideas that every basis can be extended and so on. Even the dimension. So even if you think we use this dimension and stuff formula, it was more like ideas. There wasn't much computation to prove that result. There was a little bit rank nullity, but not much. Yeah. But if you do this row and column operation, it's a full-fledged algorithm, and it takes a bit of effort to do. Yeah, so you can see the advantages of using abstraction. Okay. So now so you know what endomorphisms are. So what is an endomorphism? A linear map from a vector space to itself. Phi from V to itself is called an endomorphism, called an endomorphism of V. Yeah. So see, if there are two different things, different vector spaces, then we need a basis for both of them to write down the linear map. But if you are given the same vector space, and if I give you a basis, so one can also write down a linear map for that basis. Yeah. So this is what we want to say. So let B be a basis of V, then the matrix of phi with respect to B is basically, in the old notation, is the matrix of phi with respect to B comma B. Yeah. So this may be a silly way of writing it, but what it means is that so you say B is summation V1 to Vn, then what it means is that phi Vj, you write it as summation Aij Vi, I equals 1 to n. Yeah, because phi Vj is again in V. Yeah, so you can write it as linear combination of this. For all j between 1 and n, you can do this. So you get a square matrix. Yeah, and A is this Aij is the matrix of phi with respect to with respect to B. Yeah. And again, one can do this change of basis matrix formula. Yeah. So if you change the basis, the matrix will change. Yeah. So maybe you can tell me what the answer was. So let B and B prime be basis of V with V and sorry. So say A and A prime be matrix of P with respect to B and B prime, then what is the relation between A and A prime? Then what can we conclude? So we saw that A prime is what? Yeah, tell me, what can we conclude? So we can write A prime as PAQ for some P and Q, right? This is what the previous thing tells us. But now we are in a better, so this result told us that A prime, we can write it as PAQ, right? But now instead of, we have the same vector space, yeah? So there is a relation, uh, what was P? P was the change of basis vector from C to C prime, yeah? And Q was the change of basis vectors from B prime to B. Yeah. So what you can do here is write it as, but here C is same as B. Yeah. So P and Q are inverses to each other. So you can write it as P inverse AP, where P is the so P is basically Q, B to B prime. Yeah. So yeah. So P is basically Q. So what was Q? Let's see. So change of basis matrix from what to what? Q was change of basis matrix from B prime to B. Yeah. So here this P is basically change of basis matrix from B prime to B, where P is the change of basis matrix from B prime to B. Okay. So I'm just rewriting that previous result in when V is same as W. Yeah. That is all I'm doing. Yeah. And using these result that if you change B prime to B, then it's Q. Then if you do the change from B to B prime, then you get Q inverse. Yeah. So here it's I'm replacing Q by P. That is the only thing I've done. Yeah. So we get that A prime is just P inverse AP for some for this change of basis matrix. So in particular, P is in GLN, GL of V or GLN, because we are taking V to be the so the basis has length. Let's say GLB. So let's write it coordinate free. Okay, so invertible linear. Let's just write GLN. Yeah. Where n is the length dimension of the vector of the vector space V. Okay, is this fine?
Yes, sir.
Someone wrote a question. Sorry, I thought B and B prime are matrices. I was so you should tell me if you have some questions, Anarga. Okay. I may not hear. So now is it clear? So B and B prime are bases, not matrices. B.
Yes, sir.
Okay, good. Yeah. Okay, so maybe this is a good place to stop. Yeah. So next time we will we'll talk more about these things. And so maybe first let me stop recording.